All right, so this is, I think, October something, yes? Someday in October. I think this is the 13th lecture. For those of you who forgot, I'm Professor Miller. I'm your professor for operations research. I know it's been about a week since we've actually had a class. I don't know what's going on. It seems like all the desks have shifted a little bit outward. This must be some kind of creep or whatnot. What I want to do today is start talking about binary integer programming, or more generally, how we use linear programming to solve problems. So right now we've talked about if we have a canonical linear programming problem, we've talked about the simplex method, we've talked about how the simplex method can solve things. What we haven't done is we haven't actually talked about how would you take a problem you care about in the real world and convert it to a linear programming problem. So that's step one, is what kind of problems can we solve? Step two is how do we want to convert it? There are often many different ways you can convert a problem. We've talked about when you're coding a Sudoku, do you want to code the numbers as 1, 2, 3, 4, or as 1, 10, 100, 1,000? It doesn't really make a difference unless you're actually physically writing them down. But in terms of writing the code, in terms of running things, it can make a huge difference. And so this is the difference between theory and practice. So there could be many different ways to formulate a problem, but they may not all have the same efficiencies in runtime. So what I want to talk about first is binary integer programming. So I've actually done a fair amount of integer programming for various applications. So I've done it for a movie project problem. I've done it with some students in the past for Mount Greylock. Someone in this class is going to work with me for the elementary school. You really want to do things with integers, integer random variables. And there are two types of integer random variables we could have. So one is maybe x is in 0, 1, 2, or another is x is in 0, 1. So here I'm taking, non-negative integers. Here I'm taking binary, just 0, 1. Any thoughts as to which is better? Why?
Easier.
Why is it easier?
It's on or off.
It's on or off. Computers love on-off. Do you think that if you can do things with general integers, you can do things with binary? So how would you pass from general to binary? So if you can solve, yes?
I mean, you can map each random variable to like log tube itself, random variables that represent like the ones place, the twos place, the fours place.
Okay. That's going in the other direction.
No, it's not. Is it?
Yeah.
We're mapping top down.
What I'm saying is, if you can solve a problem where the integer inputs are 0, 1, 2, 3, 4, 5, how would you solve a problem where the inputs are just 0, 1? So I want to consider just a more restrictive problem where I now want, in addition to being just a non-negative integer, I want my integers to be at most 1. What constraint do I add? What constraint could I add to get from this general case to the specific case?
X smaller than 2.
I'm sorry?
X smaller than 2.
X smaller than 2. Or maybe add x less than equal to 1. If I put in some kind of constraint like that, if I can do this general case, I can put in a simple constraint like this and then force myself to just look at things 0, 1. The other one is, what about going the other direction? Binary to general. And this was what was just mentioned a moment ago, is you write any number in base 2. So write x as the sum of xi 2 to the I. I goes from 0 to infinity. Xi is in 0, 1. Now, in order for this to work, we do need one additional factor. What additional factor would we need? So there's one small issue going like this. How many variables would we have to use here? potentially infinitely many if we don't know ahead of time how large our numbers can be. If we know our numbers are bounded, then we're fine. And we know when we look at its binary expansion, it's going to go at most to a certain height, and we can truncate. But if our numbers could be arbitrarily large, which this would allow, so there's a small loss maybe in going from just being able to solve binary problems to being able to solve general integer programming problems. But if things are bounded, okay. So okay if bounded. In any application I know in the real world, things are going to be bounded. We have finite resources. We have finitely many things we can do. Question?
Yeah, I just don't understand why it's important that like the binary representation of the numbers be bounded when, like, because I feel like there's a finite number of, like, the binary representation is a finite number.
Right, but I want to know how many variables I have to play with.
Right, but isn't it?
If you have an infinite variable, the binary representation is not finite, right? Because you're just taking
Oh,
base 2
the
of
actual
it.
representation of the number could be.
Right,
Yeah, okay.
right. Because if I don't know ahead of time what's the maximum value of I that I could take, I have to have infinitely many variables. And now we're doing infinite linear programming, which could be fun. But I think I'd like to avoid that for now. Let's keep things finite. As an aside, I've actually talked to some people. There's a lot of great things you can do with for loops. And if you want to do a variable number of variables in for loops, you can actually do this with binary or more general b-adic representation. So let's say you want to have x1, xn all go from 0 to b minus 1. So you need to do a bunch of for loops. The problem is you don't know ahead of time how many variables you have. That's going to be something that's going to be passed in. What you do is you can count, so this is an aside, you can count from 0 to, I think it's b to the n minus 1. And in each number you convert to base b. So convert m to its base b expansion. So m would be the sum of xi b to the I, and this will now give you what each of your variables are in your for loop. So if you don't know ahead of time how many variables you're going to have to play with, as long as they all have the same range, 0 to b minus 1, we can actually do this by just counting from 0 to b to the n minus 1.
How do you know what b to the n minus 1 is?
Well, let's say you know each of the variables goes from 0 to b minus 1.
Right, but yeah. So I guess here's what I'm asking, right? We have n variables, right? We're passing in x1 to xn.
Right.
We don't know what n is.
Well, you know what n is as you're running the program. You don't know what n is ahead of time when you're writing the program. Right. So you're given n and b as inputs. But when the program is being written, you don't know ahead of time how many for statements you're going to need. It's a parameter. And so this is a really nice way to allow you to do variable for loops, or variable number of for loops. All right, so we often call these binary variables or decision variables. So it could be whether or not a plane is flying. It could be whether or not a movie is showing. The difficulty is trying to figure out how many subscripts do you want to do. So if we were doing Sudoku, what do you think could be good variables for Sudoku? Does everybody here know how to play Sudoku? It's amazing what changes over a couple of years. All right, so what would be a good variable for Sudoku? So let's say we're looking over here. What might I want that variable to be? So one thing is 0 through 9? 1 to 9. So we could do 0, we could do 0 to 8, we could do 1 to 9. That's one possibility, is to do something like that. So one possibility is maybe xi is in 1 to 9 for Sudoku. There's something else you could do rather than having 0 through 9. I could have my variables x, d, and then I would have to have some kind of way of denoting which square I'm in. So there'd be 81 squares. So maybe I ranges from 1 to 81. and D will range from 1 to 9. And what this could be is it'll be 1 if we have a D in the ith square and 0 otherwise. And now I'm just doing everything as a binary variable. So I could do Sudoku where the variable xi is the value in the ith box. Or I could do the variable is xdi, where it's 1 if we have a d in the ith box and a 0 otherwise. Or you could even have not as your variables xi, maybe xi comma j, where you have 2 indices, 1 for row, 1 for column. Does it really make a difference if I'm using xi, xij? There's a nice map from them. It's which is going to be the easiest for you to write down in whatever computer system you're looking at. Okay? Some people, I believe, have started to look at the chess problem with integer programming and trying to attack it and get both something for the chess problem and the dual of the chess problem and try to figure out when they get to optimal. This is a great, the queen problem is a great example of a binary integer programming problem. Do I have a queen in this spot or not? And I'm trying to either maximize the number of pawns that can be safely placed, or if we don't want to do that, minimize the number of squares attacked. Okay? So again, it's all a function of what is going to be the easiest for you to code. All right, so let's do a movie theater problem. So imagine you own a movie theater. What is your objective? Make money. Okay, how do you make money? Hypothetically by showing movies and selling food. Which do you think is your bigger source of revenue? Ticket sales or concession sales? So how many people think concession? How many people think tickets? How many think it might actually matter where you are in the cycle? Yeah, it could actually matter where you are. Anybody ever see Blair Witch? This was a sleeper movie from many years ago. It didn't start strong, but unlike most movies, it actually had higher demand as time passed. It was a word-of-mouth movie. I think Something About Mary might have been that as well. There's a couple of movies like this that have a different profile than usual.
Also, IMAX tickets in New York City are like $25. So like, I can't imagine people spending more than that on food.
Do you know how much money that goes?
But how much of the, okay, so the comment was that IMAX movies in New York City cost $25. How much of that $25 goes to the movie theater and how much goes to the people who own the film?
And then how much are snacks at the theaters still?
I mean, they have finance plans now for the snacks.
They have what?
Finance plans. You can pay a certain amount now and then pay a certain amount every month, and eventually you own the Diet Coke. Not necessarily the cup, but... So when you're George Lucas and the Phantom Menace comes out, I don't know, are you guys... All right, you just flunked this class. It's incredible. I mean, the only time I ever threatened a colleague at Williams was a good friend of mine. I don't mind if this is recorded. My wife was teaching out of town. I couldn't get back in time to pick up the kids. I wasn't going to be there, and I needed him to watch my kids for just a few minutes. I said, we've already watched episodes 4, 5, and 6 of Star Wars. We've now looped, and we're now on Phantom Menace. And he asked me, what would happen if he made my kids like Jar Jar? And I said I would fight his tenure. I would make sure Williams does not make a mistake of tenuring. And he agrees that Jar Jar is bad. He and I are going to be teaching a Star Trek winter study class. We agree on many things.
Have you heard the conspiracy about Jar Jar being Sith?
I have heard we could talk about this at lunch.
Like that Jar Jar is the original Sith Lord? That's a great movie, guys. Look into it. It's absolutely, it's too real.
Yeah. So George Lucas is very powerful. And when The Phantom Menace comes out, people do not know how that movie will be. I'll leave it like this because this is being recorded and I don't want to go against a potential Sith Lord. So what are you going to do if you're a movie theater? George Lucas says, I have this new movie. It's the first Star Wars in a long time. Would you like to show it? Sure, yeah. Oh, and by the way, I want you to show it on your best or your 2 best screens for at least 8 weeks, and your sound system must be at a certain level, because if you don't hear Jar Jar in the correct surround sound, you will not appreciate all the nuances of his character development, methinks. Okay? So George Lucas can run hard deals. A lot of movie theaters said, okay, we think we're going to get enough in concession revenue, and we think we're going to get enough back from the ticket sales that it's worthwhile. A couple of other movie theaters said we don't think it's worthwhile. We don't think we're going to get enough revenue from this for the length of contract you're forcing on us. We'll let other movie theaters get the big bump in the first 2 or 3 weeks, and then when things settle down, we'll have other movies that we can show. So it's a really interesting question as to which movies do you want to commit to showing? How much do you think they're going to generate? What age group do you think is the ideal customer for movie theaters? Young people. What type of young people? 14 to 20 on...
Teenagers who just are able to leave by themselves.
Teenagers who can go by themselves, probably teenagers on dates. 100% of their income is disposable. No, absolutely. I teach a class on Lego, and for a long time, Lego resisted selling to adults. And then eventually they realized, what are we doing? These people who don't have to ask mommy and daddy, can we spend money? And they'll buy 5 or 6 big Lego sets at once. We like these people. And so you really want to think, who is your market? And so how much will you get in concessions? Now, you will probably have to clean up a little bit more after kids than you will after, say, senior citizens. But I think it's worthwhile to be cleaning up. So you want to figure out what movies do you want to show, what time of day do you want to show them. I'll post some papers I've written with some marketing colleagues on questions like this. One of the biggest problems is trying to estimate demand as a function of time of day. This is where a lot of probability and statistics comes into play. This class is co-listed. So if you want to figure out what is the demand of a movie, you can try to figure, well, what kind of parameters can I describe the movie with? So what kind of parameters might you think of for a movie? Length. If this is a 3-hour film, which I think some of the Lord of the Rings might have been close to, that's very different than if it's an hour-and-a-half comedy. What else? Genre. Okay, big one. Is this a chick flick? Is it an action movie? Is it a documentary? Is it a sequel? Is there already a fan base? Or nowadays, they didn't have this word when I was young. Is it a reboot? Let's look at the 3rd iteration of Spider-Man. Are we on the 3rd iteration of Spider-Man now?
I think we might be.
Okay.
We're definitely set to.
I know we've rebooted Superman at least once, which was good because Superman 4 was horrible. Anybody suffer through Superman 4? My kids had watched 1, 2, and 3, and they wanted to watch Superman 4, and I told them, you don't want to, but they outvoted me. And they said, wow, you were right, Daddy. So, is it a sequel? Is it a reboot? Okay? There's another thing that really matters.
The rating.
So one thing is the rating. Especially if you're a little kid, you want to watch a movie that has maybe a higher rating.
Probably.
Yeah.
Makes you seem older.
Right. No, I wanted to watch Beverly Hills Cop when I was in elementary school, and my mother did not want to let me because it was rated R. And so with a straight face, I said, I've been riding the school bus for 5 years. Which word do you think I haven't heard? And she said, you can watch it. Which was a pure, I hope my mom doesn't get this tape, but it was a pure bluff. I was on a very nice school bus in a very nice town. Nobody really said anything, but I'd watch TV shows where people were scared about things like this. So one thing is the rating. There's a big thing you're definitely missing. I'm sorry?
The actors in it?
The actors in it, right? There's certain people who like certain types of actors. I like Ben Kingsley. If Ben Kingsley is in something, I really want to watch it. There's certain other actors that I would like to avoid. Okay? So there's a lot of different factors you can put in. Another big one that you're missing. Season, excellent. Right? If this is Christmas, Thanksgiving, Labor Day, July 4th, there's a couple of really good times in the year to release movies. This is not when hopefully they release the new big Pee-wee's Big Adventure or whatever it is now this time. Right? So time of year matters. Weather actually matters. In the movie theater we were looking at in the Netherlands, I know national holidays mattered. Will people be off from school? If you're a movie theater, it could also depend on how easy is public transportation to you. In this area, there's a lot of people who do not have cars in the Berkshires. How easy is it for them to get to the movie theaters? So there's lots of different factors you can do. And what you can do is you can do a massive regression. And you can try to figure out, based on these parameters, this is what we expect the movie's demand will be, looking at sales of other movies throughout the country. and trying to figure out which parts of the country might be a reasonable approximation from where you are. So I will provide that paper. It's really worth looking at as to how you would try to solve this. We will now assume that we have the demand for each movie as a function of time of day. One of the more complicated aspects is, do movies compete with each other for demand? So if you were to show, the new Star Trek and the new Star Wars movie at the same time, do you think they would be competing for the same people? Probably, right? If you show two superhero movies at the same time, there might be somebody who wants to go and see an action movie. They might not care which action movie they see. So if you're trying to figure out demand, you might actually want to have some kind of cross-term, which will be more interesting as to if these two movies show together, the demand for each one is reduced by a certain amount.
Would you worry about that, though? Because if someone comes by to see an action movie, don't you not really care which one they actually go to as long as they buy a ticket?
Well, but if I'm trying to estimate how much money will I be making when I'm trying to decide my movies, I can't just sum the demands.
You want disjoint.
So I want disjoint. And I want to try to figure out, and so you absolutely take it into account in the model. I'm just saying it's something that you really have to consider. And I've had discussions with some colleagues as to how much we should consider this. So I thought it would be fun to just try to come up with constraints. Imagine you own the movie theater. I've already told you the constraint in the past that was really killing our project. But can someone tell me some constraints you think we must have, and then we'll try to decide what we want our variables to be.
You have to show a movie every 20 minutes.
Yes. So we, I think, have a rule in the college that we must have a class starting every 50 minutes. For all practical purposes, I cannot imagine a 50-minute stretch during the day at Williams where we do not have a class starting.
4 to 6.
I'm sorry?
4 to 6.
4 to 6. But days over at 4. Days over at 4 o'clock.
Monday, like 1:20 to 2:10.
I guess we should probably say like an hour. So
Yeah.
there's no, I would say if it's an hour window, I think there's a class that starts. So that if you really like taking classes Mondays at 2, there'll be an option for you as Williams students for that wonderful 2 o'clock Monday slot. Although we do have now these strange days, these like Monday, Thursday, and these Tuesday, Fridays, and I know they start at strange times.
Those are pretty fun.
Yeah, those will start like halfway.
Right, those will start halfway through. So what do you want your variable to be as a movie theater? What do you want your indices to be? Yes?
You need something representing the number of the screens you have.
So we need something representing screens. What letter should we use for screens?
S.
Okay, so if on screen S, what else? Any other indices? The movie. If on screen S we show movie M at time t. So there's a lot of different ways to look at this. One way is to say that this is going to be 1 if on screen S movie M is playing at time t. I think there's a better thing than having it just being playing. Starting. Because if you start a movie, then you know how long the movie is. And what you could do when you're trying to figure out the length of the movie, you can also add a cleanup time afterwards. And if you want, your cleanup time does not have to be the same for all movies. Movie cleanup times could depend on time of day, and it could depend on type of movie. So I think this is a really good variable. So it's 1 if on screen S we start movie M at time t and 0 otherwise. So when you look at your times, what do you think your times are? So for instance, could I choose on screen 5, movie 7 to start at 12:15:32? So do you think it's minutes?
Well, they're integers.
They're 5 minutes.
Maybe 5-minute intervals. Definitely not more than 10-minute intervals. So I would think time is probably in 5 or 10-minute blocks. It's unlikely it's going to be in a 1-minute block. If you're doing train schedules or plane schedules, these airlines are extremely accurate. Your flight is going to be at 8:57.
They're extremely accurate on paper.
Yes, yes.
They show up all the time.
No, they're wonderful theoretically, yes. My favorite is when I called up the airlines because my flight was still delayed, and they said, well, according to our records, you took off 5 minutes ago. And I tried to wave to them through the window. I said, nope, I'm still on the ground. So we'll probably have t in 5-minute intervals. So maybe t goes from 0 to end in 5-minute steps. And maybe we'll have s go from 1 to big S, and m go from 1 to big M. You want random variables, and you want labels that are easy to look down. Big M for the number of movies, little m is going to represent the movie variable. I want to be able to quickly glance down and see what's going on. So what would be a constraint? Okay, so you only have so many movies playing at the same time. Be more specific. Okay, but you can do even better than you only have big S movies playing at the same time. So technically, how many of you have ever seen Back to the Future 2? So there's a scene early in the movie where Marty McFly's son is watching 6 channels at the same time in his house. And they've got the TVs in the future that allow you to do that. We have those TVs now. Movie theaters are not going to show 6 movies on the same screen at the same time. So when you say we have at most S movies playing, we can actually do better than we have at most S movies playing. It's related to screens. What kind of constraint do you think we would have? We have at most 1 movie playing at a time on a screen, right? So how would you represent that? So for all t, for every time, for all screens, right? So at most 1 movie on a screen. I want to make sure that there's at most 1 movie playing on this screen at this time.
Maybe fix S and then sum over M and T and see that it's just less than equal to.
Well, we wouldn't. So you're close. We're fixing a T and an S. We care about a specific time.
Could you do the sum of xs or x at certain t equals 1?
If it equals 1, what does that mean?
Less than or equal to 1.
So if you do equals 1, it means there must be a movie playing at that moment. So one is you would want it to be less than or equal to 1. And we would sum over all movies. 1 to infinity, 1 to big M. Does this guarantee that we have at most 1 movie playing on screen S at time t? No. What does this guarantee? We have at most 1 movie starting at time t on screen S. I want to make sure we have at most 1 movie playing. Right? So we have to be a little bit more careful. So what I'm going to do is I'll keep the sum over M. M goes from 1 to big M. And now, instead of using time t, I'm going to use tau. Because tau is a Greek letter that looks a lot like a T. What do you think the range of tau should be? Tau goes from what to what? I'm sorry, the duration of the movie. And it should go all the way to what time?
So from minus start time of the movie, like +1 to the end time of the movie. Right? Because we have to check before if there was a movie starting.
Correct.
And
Right.
and
So give me the range for tau.
So the minus start time of M.
Okay.
Current time minus.
Good. So current time minus the runtime of movie M. Or maybe minus 1. You know, I'm not going to worry about something like that. And it goes all the way up to time t. So if I choose to start a movie in that window, it will still be playing at time t on screen S. So this is what I love about linear programming. It's very easy to write down constraints like this. This gives you a constraint that at each moment in time, we have at most one movie playing. So this is called a hard constraint. Hard does not mean that it is difficult to incorporate. Hard means that we must follow this constraint. Okay? If you are doing airlines, you cannot have the same plane traveling from Albany to Atlanta and at the same time traveling from Los Angeles to San Francisco. You know, as much as you may want to do that. There are other constraints in the airlines. You know, pilots must have a certain amount of downtime. That you can violate. You might get into trouble, but you can violate something like that. This is one that we can't violate. Can someone give me another constraint that we can't violate? So this is, at most, one movie is showing on a screen at a given time. What's another constraint? This is the only constraint we have to worry about if we own a theater. That's a hard constraint, a hard constraint. There's another natural hard constraint, and I will tell you there is a potential way to get around it. But you should view it as a hard constraint. With modern technology, it's harder to get around it. Anybody else have any other thoughts about what we must do? Yes?
You can only sell as many tickets as there are.
Oh, good. So one thing is going to be capacity.
Whoa, my local movie theater actually is like half, cut the number of seats by like a quarter, like down like 25%.
They also expand
Okay.
the seats like nice cushy chairs.
Right. All right. So one thing is in terms of how much money you get, there will be some issues. And then it becomes a very fascinating question. If you have too much of a demand for a movie relative to its capacity, you know, for the screen you're showing it in, what happens to those extra people? Do they migrate to another movie? So that will actually come into the objective function. So we'll hold on to that for a moment for the objective function. There's other constraints. Can anybody think of another constraint?
Another hard constraint.
Another hard constraint. So you were giving me a constraint about a screen. On this screen, we can have at most one movie. Think about a constraint now for a movie. So we were fixing a screen. Now let's fix a movie. What can you tell me must be true about a specific movie?
Well, it can't be shown on more than S screens.
It can't be shown on more than S screens. You can probably do a little bit better than it can't be shown on more than S screens.
You could show it on more than one screen, though.
At the same time?
Yeah.
Why not?
Oh, they wouldn't start at the same time.
Well, they could start. So here's a question. Can you show the same movie on multiple screens?
Yeah.
Yeah.
How?
Oh, you have to own multiple.
You have to own multiple copies.
Oh.
So what you... Oh!
You have to like buy.
So one of the things you could do is you have to buy multiple copies. So you could... And so when you do it as classification, I'm not saying the movies are distinct. I'm just saying we have M movies. Some of the movies might actually be the same. It might be copy 1, copy 2. And for a lot of purposes, we don't really care if we're showing copy 1 of Lord of the Rings or Phantom Menace or copy 2. In the old days, they had this thing called film.
So a movie only has one.
And so a movie only has one screen. So how many of you know what old film is? Where they had the reels and they would put it in and they go flip, 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 flip. You could have long movies that would be on 2 different reels. And sometimes they would have bad transitions. What you could potentially do if you have it on 2 reels is you start you play it for a little bit, and then as soon as you switch into reel 2, now reel 1 is available, and you can move that to another. So the question is whether or not you are contractually allowed to do that, or if you have to pay. And if you have to pay, do you have to pay as much as if you had 2 copies, or do you just pay somewhere between 1 and 2 copies in terms of things back?
Would you consider that showing 2 separate movies?
The way I would view it is the following, is you have 2 movies, reel 1 of Lord of the Rings and reel 2 of Lord of the Rings. And I would have some constraint. If you show reel 1, then you must show reel 2 immediately afterwards on the same screen. Okay? I would then put that as a constraint, and then I would have 2 things like this that I could, and I would probably have some constraint that you're not going to start reel 2 unless reel 1 has already been played on that screen. So you could put in constraints like that, or you could just say we have 2 different things. So after you play with this for a while, the constraints become fairly natural. So we'll do at most 1 screen for a movie. So this would be for all times, for all movies. We want to make sure it's showing on at most 1 screen. So somehow I'm probably going to have an SM. And then do you think I want a T or a tau? Tau. And then I should probably sum over all screens. Oh, so at most 1 screen for a movie. So 1 to big S. So I want to make sure that at a given moment in time, this movie is only playing on 1 screen. So now I need to look at my times, and my tau will go from the time minus the runtime of the movie to the current time. So will this work? So now I range over all screens, and I see, is movie M playing on that screen? If it's playing on that screen, it had to be started in that window. Is this what I wanted? So this should be less than or equal to 1. So you can keep putting in more and more constraints like this. The question, of course, is how easy is it to solve constraints like this? How easy is it to solve linear programming? So for those of you who are in computer science, you know that linear programming is not easy to solve. But we can come up with really good approximations to the solutions very rapidly. And that's why I love linear programming so much. For a lot of things, we don't have to have the optimal solution. We just have to be close to optimal. And that is more than enough. So there's a lot of other constraints you can have. I'll just mention a few. You might want to control how many movies start at the same time. Why would you want to control the number of movies that start at the same time?
You wouldn't want all of them to start, because then you would have like a period where you couldn't, for like 2 hours or something, no one could come in.
So one thing is if all the movies are starting at the same time, that could make it hard for the people who arrive at a different time. What else could be a problem with that?
Longer lines.
Longer lines. You know, do we care about the experience of our patrons? You know, to some extent, yes. You know, enlightened self-interest. You want to make money. You want people to have a pleasant experience. Long lines are not pleasant. What would you have to do if you had long lines? Open more ticket windows. What happens if you open more ticket windows? You now have to pay more employees. So what you would rather do is you would rather spread out how much time people are waiting in line by having people staggered when they come in. And if you do that, then you can have fewer employees working. So what else might you want to do? So that's when movies start. What else might you want to stagger? When they end. Why might you not want all the movies to end at the same time? I can think of 2 reasons. Yes? Yes. I mean, you could put a little sign, please take all your rubbish with you when you leave the theater. Yeah, exactly, yes. So that's not going to happen. So the more movies ending at the same time, the more people you're going to need because they're going to have to all come in and clean up the theaters at the same time. There's another reason why you want to stagger when movies end.
Make sure people actually leave.
So what is potentially to make sure people leave? You could have, there are people who try to go to multiple showings.
If you all get out at once, it could be really easy to get a crowd like walk back into a theater.
Exactly, yes.
Would it also then ensure that the next round will all start at the same time unless you stagger re-stagger?
So one possibility is if they're all ending at the same time, you could potentially have a staggering problem. But there's other reasons, yes.
Like bathroom?
Bathrooms. So I was wondering if anybody was going to mention the bathroom issue. If you look at gas stations right off the highway, often high prices and often could be a very long line in the bathroom because this is where people all go at the same time. If all the movies are ending at the same time, you could have everybody hitting the bathroom at the same time. You could also have large crowds of people walking through the building at the same time in the same area. So what some theaters will actually do is they will try to stagger which parts of the theater do movies end. So you don't have all the people rushing out in the same area. That's often a constraint you put in. So there's lots of things like this that you can do. It's a really good exercise to go through and try to write some of these down. Let's just talk a little bit about the objective function. So we need some parameters. What's a parameter that you think we might want? When we're trying to figure out how much money we make. Yeah. So we already have the list of movies 1 through M. We need new parameters. Ticket cost. So maybe we need maybe PM for the price for movie M. Now, you could have different ticket costs. You could have one cost for kids, one cost for college students, one cost for adults, one cost for senior citizens. So you can have lots of different costs. So we'll just do P is the price of admission. This is the simple model where everybody pays the same. This is not what the movie theaters will do. But it will just make things a little bit easier as we're explaining here. You can add the extra stuff without too much more work. What else do you think we need?
Like the price that it costs to buy a movie.
So one is the cost of the movie. And so we would need to figure out maybe how much we're getting per person. So what we can do over here is price of admission. What we'll do is we'll get price theater keeps per person. And there's a lot of different ways to look at this. So do we have to pay the movie owner a fixed fee up front for the right to show the movie and then additional money per ticket sold? In which case you could have a fixed cost as to, do we even want to have this movie? We might also have certain movies that we've already bought because we have previous weeks. And so you really don't want to maximize over just one day. You want to maximize over an extended period of time. So we can start to refine these things and we can have a more advanced model. Yes?
Back up on that.
Sure. So maybe George Lucas says, if you want to show Phantom Menace, you owe me $50,000 for the right to show it, and then 60% of the ticket costs, of the ticket revenue in week 1, 55% in week 2, 50% in week 3. And you often have structured deals like that, where the longer the movie's been out, the more of the take the theater gets to keep, but the smaller the take is.
So we're assuming that we're going to follow our schedule based on
Exactly. Yep, and so we could actually have things like this that will depend not just on the time of day, but also on the week. So for instance, matinees are often cheaper. People don't really want to go to the movies at certain times of day, so to make it more appealing, we'll lower the cost. What other parameters might you want? What? So concession price. So maybe C is concession per person. And again, right now I'm just assuming it's the same concession for everybody. That's not a reasonable assumption. What else?
I would just say we could have something like K for like the fixed cost of showing a movie, including like which includes like cleanup,
Right.
and setup, things like that.
So you could have cleanup costs, setup costs. There's a really big one that we should incorporate, and it's been mentioned a little bit before. I think you mentioned it earlier. And I said, when we get to the objective function, now you can say it.
Oh, the amount of seats available.
Seats capacity. We'll say case of S for capacity of screen S. My spelling has always been bad. Okay? So that's obviously something that could become extremely important. What else? And this is a parameter I talked about, the demand for movie M at time t. Right? So we need to figure out what these demands are. And this was actually someone's PhD thesis, was trying to figure out what's a good regression model to predict what these values should be. And that's a key input in something going on here. So then we would want to try to figure out how much money we're making. And so it really doesn't matter if we maximize or minimize. The theory is really the same. All right? I will just try to maximize revenue, or technically maximize profit. So how would we figure out how much money we make? Now, I think we should have some term that will be the sum over all times, sum over all screens, sum over all movies. And then if we start showing on screen S movie M at time t, we get P dollars for each person. And how many people do we get? Hopefully K sub S, but that would be only if we have complete capacity filled.
We get DMT.
So that's,
We get DMT divided by number of screens we have it showing on.
well, each movie is only showing on one screen. And then things can be complicated if you have 2 copies of Lord of the Rings. So let's assume for now that we don't have 2 copies of a movie. So I'd love to just put in DMT. But what's the problem with putting in DMT?
Can we do the minimum of
So if we do minimum. So what we could do here is do minimum of DMT and the capacity. Do we have to worry about now putting in minimum as a linear programming constraint? Do we have to figure out how to handle the minimum function? Why not? It just gives you a number, right? This is not one of our random variables, right? DMT and KS are fixed. If you want to confuse a calculus student, ask them to take the derivative of x times the log base 3 of 5 or something like that. And it's amazing how many Calc 1 students will use the product rule. They don't recognize the log of 5 base 3 as a constant. This is a constant. Okay? So this would be the start of the objective function. Yes? Okay.
Maybe go P plus C or something.
I'm sorry?
Maybe we should go to P plus C.
Yes. So, yes, this should probably be P plus C. Right. Or you could have a separate term which would be the concession revenue, but I agree it would be nice to just fold this in. And then what you would do is you would really want to almost break up at some point your population. All right, so I think we're going to have a guest speaker on Monday. I'm not sure if that's going to take the whole class, but then after that, we'll talk a little bit more about how you formulate constraints, and we'll talk about things you can do in integer programming. So it turns out as soon as you add these binary integer variables, a lot of nonlinear constraints can be done linearly at the cost of adding more variables. So you can handle the absolute value function linearly, maximum minimum linearly, or and linearly at the cost of adding more variables. And we'll see if that's worth